Electricity can seem kind of confusing at first, right? We flick a switch, a light turns on, it almost feels like magic. But underneath all that magic, it really comes down to three foundational words: voltage, current, and resistance. Once you get a handle on these three things, the whole invisible world of electricity just completely opens up and makes sense. So, welcome to The Explainer. Today we're going to break these concepts down in the absolute simplest, most direct way possible. Let's get right into it.
First off, I want to start by asking you a quick question. Do you think a light bulb uses up the electricity from a battery? Honestly, it's a supernatural thing to assume. I mean, in our everyday lives, we're constantly talking about our phone batteries dying, or saying a device is out of juice. It totally feels like the battery is this tank of electricity that just drains away. But, as we'll see today, that deeply ingrained intuition, it's actually a massive scientific misconception.
Here is our roadmap for the explainer today. First, we'll look at understanding electric current. Second, voltage, which is the driving push. Third, resistance and Ohm's law. Fourth, we'll compare series versus parallel circuits. And finally, we'll wrap up with some real-world electricity applications.
All right, Section 1, Understanding Electric Current. Let's dive in. Okay, so there is a huge contrast here between common myth and scientific reality. The myth is basically that a battery stores up electrical charge, like a bucket full of electrons, and just pushes them out into an empty wire. But the reality? Delocalized electrons are actually already sitting right there inside the wires of the circuit. A battery is really just a store of chemical energy, not a store of electrons. It just supplies the energy to make the electrons that are already waiting there start moving together.
And that movement brings us right to our first precise definition. Current is the rate of flow of electric charge around a closed circuit. We measure this in amperes, or, we usually just shorten it to amps. A really great way to visualize this is using a stopwatch analogy. Just imagine picking one single point on a wire, grabbing a stopwatch, and counting exactly how many electrons flow past that specific point every single second. That rate of flow, the flow of charge per second, is exactly what current is. So if more charge flows past your point each second, boom, you've got a larger current.
Moving right along to Section 2, Voltage, the driving push.
So, if we know that those electrons are really just sitting stationary in the wire and current is the flow of that charge, well, what actually gives them the energy to suddenly start moving? What provides that push?
The answer is voltage. You might also hear it called potential difference. Voltage is defined as the energy transferred per coulomb of charge, and yep, it's measured in volts. To keep things super simple, it's basically the push that drives the current around the circuit. The higher the voltage, the stronger the push. If you want to get specific, a voltmeter measures the energy the electrons have right before they enter a component, like say a light bulb, and then measures it again right after they leave. Those electrons give up some of their energy to make the bulb shine, right? So they have less energy coming out than they did going in. And that difference in energy, that is exactly what voltage is.
All right, Section 3, Resistance and Ohm's law.
Okay, so we've got the charge flowing, and we've got the push driving it. Now let's see what happens when the circuit pushes back. This is resistance. It's literally anything that opposes the flow of electric current in a circuit, and we measure it in ohms. You can kind of think of it like a narrow, squeezed section in a water pipe. If the resistance is high, it is way harder for the electric charge to flow through. But if the resistance is low, the current just flows super easily. Keep in mind, everything in a circuit has at least a little bit of resistance, even the wires themselves. But specific components, like bulbs and resistors, are designed to provide a lot of it.
And here is where our three foundational words beautifully come together in Ohm's law. It states that voltage equals current multiplied by resistance, or V equals I times R. Honestly, this is one of the single most important formulas in all of physics. It shows us that if the voltage, that push, goes up, the current goes up too. But if the resistance, the opposition, goes up, then the current goes down. They are perfectly, mathematically locked together in this little dance.
Now, knowing the formula is great and all, but applying it is where the real magic happens. Let's quickly walk through the balance method to mathematically rearrange this formula. Say we want to find the current. We start with V equals I times R. To get I all by itself, we just divide both sides by R. And the result? Current equals voltage divided by resistance. Being able to easily manipulate equations like this is an absolutely vital skill for working scientifically. Plus, it completely saves you from having to memorize a dozen different formulas.
Let's actually test that out right now. Imagine a really simple circuit. Let's say it has a battery pushing with 6 volts and a resistor pushing back with 2 ohms of resistance. Using our newly rearranged formula, we literally just take our 6 volts and divide it by our 2 ohms. The result? A current of 3 amps. See? It really is that straightforward when you just plug it into the formula.
Let's jump to section 4, series versus parallel circuits.
So how do all these rules shift when we change the actual physical layout of the circuit? Well, look at the differences here. In a series circuit, which is just one single continuous loop, the current is exactly the same everywhere, but the voltage, that energy push, gets shared between the components. Now look over at the parallel circuit, which has multiple branches. The rules totally reverse. The current splits between the different branches, but the voltage is exactly the same across all of them. It's pretty cool. What's constant in one type of circuit is actually shared in the other.
Now, here is a highly counterintuitive fact that trips a lot of people up. If you add more resistors to a parallel circuit, the total resistance actually goes down and the overall current increases. I know. How can adding more things in the way make it easier for electricity to flow? Well, think of a motorway. Adding a parallel branch is essentially like adding an extra lane to a motorway. Even if that new lane is a bit bumpy, which represents our resistance, it is still a whole new path for the cars or the electrons to travel down. Because there are simply more paths available, the total resistance of the whole entire system drops, and way more current can flow overall.
Okay, finally, section 5, real-world electricity applications.
You know, voltage, current, and resistance aren't just abstract ideas. They are the invisible mechanics powering literally everything around us. Take your electric kettle. It needs a massive current to transfer enough energy to boil your water quickly. Meanwhile, your phone charger acts kind of like a manager. It carefully steps down the voltage coming from your wall so that a safe, very specific current flows into your phone battery. And the lamps around your house? They totally depend on having the exact right amount of resistance in their filaments or LEDs so they glow brightly without just immediately burning out.
Which actually brings us completely full circle back to our very first concept. As this quote perfectly summarizes, current is the rate of flow of charge and is conserved. It is never used up. The electrons flow out of the battery, they transfer their energy, their voltage, to the bulb, and then they flow right back around to the battery to pick up more energy. The current flowing in is exactly equal to the current flowing out. Literally only the energy is transferred.
As we wrap this up, I want to leave you with one final thought. Take a second and just look around your room right now. Think about the phone or the tablet or the monitor that you are watching this explainer on. It is working because electrons are flowing. They're being pushed by a specific voltage, and they're being controlled by a precise resistance. How exactly are those 3 foundational pillars working together in your hands at this exact moment? Think about that for a bit. Suddenly, the invisible world of electricity isn't just magic anymore. It's beautifully logical. Thanks so much for learning with me today.